Lecture 22, Niobium, Superconducting Stability. Picture a pipeline in winter, stretched like a steel violin string across frozen ground. The welding crew is moving fast because cold delays do not bill by the hour, and the inspector is measuring the heat-affected zone with a practiced glance. Everything depends on whether the pipe can hold its temper, tough at low temperatures, ductile enough not to crack, strong enough to stay thin so you can lay more miles per truckload. The trick is not a splashy alloy overhaul. It is a whisper. A few hundred grams of a grey metal per metric ton of steel. That whisper is niobium, and it is the difference between needing a wall thickness you can barely bend and a wall thickness you can cold, form, weld cleanly, and coil like ribbon. You cannot see it on the mill floor. But you can feel it when the torque wrench stops sooner than expected, when the bending machine hits its radius on the first attempt, when the call from integrity management never comes. Niobium is a soft-spoken extrovert in the periodic world. It is shy in pure form, bluish-grey, ductile, corrosion-resistant, content to sit quietly without oxidizing itself into dust. But let it mingle in the right crowd, iron in particular, and it becomes the social organizer that turns a boisterous party into a ballet. A few parts per million in the melt and suddenly grains are refined, recrystallization is tempered, carbides and nitrides precipitate like bouncers at the doors, and the entire microstructure behaves itself during rolling and welding. Metallurgists are not mystics, they will tell you what is happening in plain language. Niobium forms tiny, stable compounds, niobium carbide and niobium nitride, that pin grain boundaries, keep austenite from misbehaving during controlled rolling, and hand you strength without taking away weldability. You get yield strength where you want it, toughness where you need it, and a finish the press shop will not curse. Automotive engineers translate that into lighter beams and crash rails, pipeline engineers translate it into miles per coil and bend radii that do not blush at 30 below degrees Celsius. In pure chemistry terms, niobium is an early transition metal with a taste for a 5+ oxidation state and a habit of forming sturdy oxides. The oxide that keeps showing up in your processing flowsheets is niobium pentoxide. It is a ceramic, hard and indifferent, but it is the gateway to both ferroniobium, the workhorse alloy that steals drink by the ladle, and to the rarefied world of ultra-pure niobium for superconducting hardware. Niobium's electron count and lattice parameters are suited to forming intermetallic compounds that either strengthen the daylights out of nickel-based superalloys or lose all electrical resistance at cryogenic temperatures. So the same metal that lets you slim down a truck's frame rail also sits at the heart of the magnets that steer particle beams and the wire that allows magnetic resonance imaging machines to hum along dependably. That range is not an accident. It is a function of a metal that is amicable in the melt, obedient in oxide chemistry, and fundamentally a team player. Geologically, niobium prefers to be born in odd neighborhoods. If you are looking for a simple ore horizon like an iron formation or a classic porphyry copper system, you will be disappointed. Niobium clusters in carbonatites, igneous intrusions rich in carbonates, and in related alkaline complexes. Think of carbonatites as magma with a sweet tooth, rich in calcium and rare elements, crystallizing unusual minerals as they cool. One of those is pyrochlore, a calcium niobate that is niobium's most important ore mineral. Another is columbite, an iron manganese niobate that often carries tantalum as a co-star. The geography of these rocks is not random. You tend to find carbonatites as old pulses in the crust, sometimes weathered into laterites where the chemistry has leached away the unfaithful and left a niobium-rich residue. That silhouette, carbonatite intrusions, lateritic blankets, pyrochlore grains liberated by careful milling, explains a lot of the modern niobium map. According to the United States Geological Survey, the great majority of primary niobium comes from such carbonatite-hosted deposits in Brazil, with a smaller but persistent contribution from Canada. The United States Geological Survey has been repeating some version of that sentence for years because it keeps being true, which is both reassuring and a supply chain raised eyebrow. The name you hear most often in this context is Companhia Brasileira de Metalurgia e Mineracaro, better known by its initials. Company materials from that Brazilian producer describe a single integrated complex at Araxá in Minas Gerais that mines a weathered carbonatite, concentrates pyrochlore, and transforms it into ferroniobium and niobium-bearing chemicals that most of the steel world quietly consumes. You will find a similarly themed but smaller story at Niobec in Quebec, evolving through owners and expansion ideas. These are not mining districts dotted with dozens of juniors. They are a short cast of characters with outsized roles. If you stand at the edge of a carbonatite laterite and watch the process in your mind's eye, it begins with beneficiation so gentle it feels like a spa day. Crush, grind, float. Pyrochlore is liberated and concentrated by froth flotation, coaxed away from gangue minerals that want to follow it into the froth. Metallurgists tune collectors and depressants with the patience of a barista dialing espresso grind size. The objective is not an obscene grade, it is a stable, clean concentrate that will behave in the chemical plant. From there the chemistry takes over. Historically, niobium processing leaned on fluoride chemistry. Pyrochlor would be broken down with hydrofluoric acid, forming complex niobium fluorides that can be selectively separated from lookalike elements. Tantalum is the usual suspect, by solvent extraction. Modern flowsheets, as described by operators and patent literature, work hard to loop reagents and avoid open-ended acid consumption. They also exploit chloride and alkaline routes where the mineralogy permits, sifting niobium into a clear stream and letting impurities fall by the wayside. You can read the unit operations as a sequence of verbs: leach, extract, strip, precipitate, calcine. The precipitate you want at the end is niobium pentoxide, clean, well-filtered, eager to be reduced. The next choice is whether you are a steelmaker's friend or a physicist's enabler. If the destination is ferroniobium, the pentoxide is reduced aluminothermically in a controlled, energetic reaction that pairs aluminum's appetite for oxygen with niobium's willingness to let go. The result is a cast alloy ingot, typically around 60% niobium by weight, with iron as the balance, that can be sized and shipped to steel mills. If the destination is niobium metal for superconducting components, the path is fussier. Niobium pentoxide is reduced to metal, through a sequence that can involve chlorination to niobium chloride and reduction with sodium or by direct metal oxide reduction, followed by electron beam melting to achieve electronic-grade purity. It is not simply a question of how pure. It is a question of how pure in the right way, because superconducting radio frequency cavities, acknowledging that acronym once and then returning to the full name, care about impurities at parts per million levels that affect residual resistivity and microscopic defects that wreck quality factors. The metallurgical cleanliness that makes a pipeline steel weld go smoothly is demanding, the cleanliness for a cryogenic cavity is obsessive. Why does niobium play these particular roles so well? In steels, the answer is the choreography between precipitation and recrystallization. During thermomechanical processing, niobium in solution delays the recrystallization of austenite, keeping grains pancaked under the rolling mill instead of letting them round back out too early. At the same time, niobium forms nanoscale carbides that precipitate at just the right moments to pin dislocations and lock in strength. That is how you get high-strength low-alloy steels, sometimes abbreviated as HSLA, and yes, we will use the full name, in pipeline grades, automotive frames, ship plates, rebar, and structural shapes that are stronger yet more weldable than their older, brute-force carbon steel cousins. The beauty is not a big dose of alloying. It is a sprinkle plus process control. You can raise yield strength without resorting to sky-high carbon, which keeps weldability and toughness in acceptable lanes. If you actually need a home you can live in, you pick materials that weld without drama. Niobium gives you that. In nickel-based superalloys, niobium is an architect of precipitates that act like rebar in concrete on the nanoscale. The famous case is a workhorse alloy used across aerospace and power generation, where niobium participates in a strengthening phase that resists creep at moderately high temperatures. It is not the only strengthening mechanism in town. Aluminum and titanium also form their own ordered precipitates, but niobium's presence tunes the balance between strength, ductility, and heat tolerance that designers covet for turbine discs, bolts, and hot section widgets that cannot fail gracefully. Engineers will argue long into the night about which alloy variant belongs where. Niobium is in that conversation not as a celebrity cameo but as a regular. Superconductivity is a different personality entirely, but it is still the same metal. Niobium transitions into a zero-resistance state at a temperature reachable with liquid helium, and when alloyed with tin or with titanium it forms compounds and solid solutions that carry hefty currents in magnetic fields that would humiliate older superconductors. That is why magnetic resonance imaging machines rely on niobium titanium wire to wind their magnets, and why high-field research magnets and accelerator magnets lean on niobium tin for performance beyond the comfort zone of plain niobium titanium. Laboratories and magnet makers publish those phase diagrams and critical current curves like proud parents sharing growth charts. The point for our purposes is simpler. The supply chain for superconductivity starts in the same carbonatite dirt as the supply chain for pipeline steels. One ore body feeds a hospital and a hydrotest yard, which is an economic and geopolitical curiosity all by itself. If you are tempted to believe that niobium must therefore be a commodity circus of price spikes and speculative bubbles, you will be surprised. The niobium market has behaved for decades like a small club with cordial rules. The major Brazilian producer sets the tone with long-term contracts, great stability, and volumes targeted to steel demand rather than to the whims of day traders. According to public descriptions from the company and industry analysts, that is by design. You keep the price steady enough that designers keep specifying niobium, and you invest in downstream applications so the pie grows rather than whipsaws. There have been jolts, maintenance outages, expansion lags, the occasional murmur from a new project, but nothing like the drama you see in cobalt or vanadium. This does not mean niobium is invulnerable to shocks, it means the club has incentives aligned around boring reliability. Boring is a compliment when welders are involved. Supply chain concentration is the eyebrow we raised earlier. When a single company in a single district supplies most of the world's ferroniobium, that is efficient, but it is also a single point of failure. Governments notice, procurement officers notice, so do competitors in alloy design who would cheerfully substitute vanadium or titanium if given the nudge. According to the United States Geological Survey, alternative sources exist. Canada's mine has chugged along for years, and various African and Australian prospects are regularly dusted off for feasibility. But the Brazilian carbonatites are so large and so well understood that they anchor the market. The paradox of criticality applies. Niobium is critical not because every device depends on it, but because a few major sectors do and the upstream is concentrated. That is why you see quiet policy interest, strategic stockpile reviews, friendly visits to Araxa, research grants for process improvements and for new niobium-bearing battery materials that might someday broaden demand in a way that justifies more diversified supply. Batteries are where niobium's public image becomes experimental in a way that excites conferences. Several research programs, some sponsored or publicized by the Brazilian producer, focus on niobium oxide and niobium-rich complex oxides as fast-charging anode materials. The pitch is simple. Niobium's crystal structures can host lithium ions rapidly without the kind of volume change that pulverizes graphite or silicon, trading off some energy density for power and cycle life. Pilot cells have been demonstrated in the literature, and companies have announced prototypes aimed at buses, industrial vehicles, and grid applications that prefer brutal charge rates over maximum kilowatt-hours per kilogram. The distance between promising papers and gigawatt-hour production can be measured in factory years, but the direction of travel is clear enough that it shows up in corporate roadmaps. If even a modest fraction of this becomes commercial, the demand blend tilts away from almost all into steel, toward still mostly steel, plus a meaningful battery niche, which would ripple through mine planning and the geopolitics of who cares about niobium. Before we let the techno-optimism bloom, it is worth remembering that niobium's recycling story is prosaic. In steel, niobium is fully recycled in the sense that steel scrap cycles endlessly, but the niobium atoms ride along anonymously. They are not recovered as niobium, they are distributed. This is not a scandal, it is a mass balance. The content per ton is tiny, and there is no economical way to spike a ladle with scrap just to hit a precise microalloy addition. You still need primary niobium to hit your targets. At the high purity end, superconducting hardware can in principle be recycled into niobium feedstocks, but the streams are small and specialized. The circular economy case for niobium is therefore honest and unglamorous. The metal's major use is in a host where the host recycles. That helps overall sustainability metrics, it does not free you from the mine. Environmental and social constraints follow the geology and the chemistry. Carbonatite mining is not strip-mined coal, it is quarrying and open-pitting through weathered, sometimes clay-rich laterites into hard rock. Tailings are managed like other hard rock operations, with the twist that reagent loops in the chemical plant must be tight, especially where fluoride chemistry is used. Operators talk publicly about closed-loop hydrofluoric acid recovery and neutralization schemes precisely because nobody wants fluoride wandering off-site. Water management in lateritic settings and dust control in dry seasons are standard issues with local textures. According to company sustainability reports and independent audits where available, the leading producer invests heavily in reagent recycling, tailings stability, and community programs, partly because it is the right thing to do and partly because when you are the face of a global market, you cannot afford a visible stumble. None of this absolves the operation from the physics of moving rock and the chemistry of dissolving oxides. It means the externalities are down to engineering and governance rather than wishful thinking. If you talk to design engineers, you hear a different kind of constraint. Substitution thresholds. Niobium's edge in steels is real, but vanadium and titanium are not imaginary. A small change in section thickness or a different thermomechanical schedule might let a designer hit the same performance with vanadium microalloying or with a different phase transformation strategy. In practice, the choice is path-dependent. If a mill has deep knowledge of niobium-bearing rolling schedules and weld procedures, niobium stays. If a mill is invested in vanadium additions and has a supply contract it likes, vanadium stays. The world does not optimize from first principles at each purchase order. It sticks with what works and shifts only when cost, availability, or a big performance carrot forces a rewrite. That is where Niobium's calm pricing posture has paid dividends. Keep the surprise index low and the specification inertia works for you. The other place substitution appears is in superconductors. The race to higher magnetic fields has drawn in high-temperature superconductors whose critical temperatures and field tolerances outgun niobium tin, at least on paper. In practice, the price, manufacturability, and mechanical quirks of those ceramics keep niobium tin and niobium titanium busy. Hospitals do not rebuild magnet rooms on a whim, accelerator upgrades are grand projects on decade scales. Niobium continues to win not because nobody can beat its physics, but because it lives at the intersection of good enough performance, known manufacturing, and acceptable cost. That is the unglamorous sweet spot where materials earn their keep for decades. You can think of the niobium supply chain as a narrow river with a huge delta. Upstream is concentrated, almost a monoculture. Downstream spreads out into pipelines and automobiles, turbines and medical magnets, salt-sprayed bridges and shiny appliances that never admit to their microalloy secrets. Control sits close to the mine because the chemistry is specialized, the quality requirements are finicky, and the customers are risk-averse. That reality has shaped the market structure, a leading producer with long relationships, a few secondary sources that matter more than their market share suggests because they keep optionality alive, and a constellation of research efforts that might, over time, widen the river upstream by creating new demand profiles that support new mines. The hook we began with, the winter pipeline, the whisper of alloy, matters because it shows niobium's odd superpower. It is not a headline material. It is a design enabler. It buys you thickness you do not need to carry, welds that behave, and safety margins that survive real-world abuse. Engineers who win with niobium do not brag about niobium. They brag about weight saved, about bend radii achieved, about inspection reports that came back boring. In a century that loves flashy materials breakthroughs, niobium's promise is that quiet excellence still scales. Picture the ladle car easing under the continuous caster. The melt shop is loud, but the choreography is unhurried. You can smell the slag, you can feel heat bouncing off your safety glasses. A crane operator dips the teeming ladle just so, and the steel begins its quiet fall into tundish and mold. Only a few minutes earlier, a tech added a scoop of what looked like dull, metallic gravel into the converter stream. That was ferroniobium. Not much. A few kilograms in a heat that weighs like a small skyscraper, and yet it will decide whether this coil meets spec after miles of rolling, whether it welds without drama on a windy job site, whether some future inspector's ultrasonic probe finds a ghost or a defect. Niobium does not arrive with a marching band. It sidles in late, dissolves into austenite like an unassuming guest, and then, when the hot work starts, behaves like a disciplined stage manager who keeps every scene change on time. If you follow that same heat to the roughing stands, the niobium story becomes kinetic. Thermomechanical controlled processing, saying the phrase in full because it ends the syllables, is all about timing. You hold the slab at a temperature high enough to dissolve niobium in solution, then you reduce at just the right sequence of passes so the austenite grains are flattened but not allowed to recrystallize too soon. Niobium helps by slowing down that recrystallization. It does so not by magic but by chemistry. Niobium atoms in solution make it energetically harder for grain boundaries to migrate. Then, as the steel cools through critical transformations, niobium carbide and niobium nitride precipitate in a drizzle of nanoscale particles that pin dislocations and keep strength where you want it. If your coiling temperature is wrong by a few tens of degrees Celsius, you pay for it later. If your coiling temperature is right, the ferrite that forms is fine, tough, and obligingly strong without needing excess carbon. You get yield strengths in the several hundreds of megapascals in sections thin enough to bend cold and weld happily. No lecture hall diagram can capture the satisfaction when a finishing mill run goes exactly to plan and the tensile bars come back boringly compliant. Welding is the practical truth serum. You can hype any alloy in a brochure, you cannot fake a heat-affected zone. Niobium gives you a hand here too. Lower carbon for a given strength lets you keep carbon equivalent down, which keeps hydrogen-assisted cracking out of the conversation, or at least on a shorter leash. In the heat-affected zone, niobium carbide and niobium nitride resist grain growth that would otherwise turn tough steel into brittle gossip. You still respect preheat and interpass guidance, you still control heat input like an adult. But the material itself is predisposed to behave. When pipeline contractors talk about field bends that work the first time in January, what they are really praising is microstructure discipline enforced by a few hundred grams of niobium per metric ton of steel. Automotive engineers transmute the same physics into different bragging rights. A side impact beam that refuses to buckle early, a B-pillar that lets you meet crash targets without adding a kilogram, a frame rail that stamps cleanly instead of springing back like a bow. The playbook is familiar: solution niobium during hot rolling, a controlled precipitation sequence, and then a transformation path that lands you in a cocktail of ferrite and bainite whose morphology is tuned by the rolling schedule and subsequent cooling. The difference is in the later steps: cold forming, coating, sometimes a press hardening step for components that need martensite at the finish line. Niobium does not object. It comes along quietly, adds to the precipitation hardening toolbox, and retires every ounce of excess carbon that would have made the welders curse. If you have ever listened to a stamping engineer complain about springback, you know why this matters. Consistent, fine grains keep geometry honest. Step back to the chemistry plant that made that ferroniobium scoop and the calm dissolves into unit operations. Start with pyrochlor concentrate from a carbonatite. The purpose of beneficiation is not to produce dual-grade mineral, it is to deliver a feed that will react predictably in leach circuits. Historically, hydrofluoric acid was the blunt instrument that cracked pyrochlor open, turning the niobium into complex fluorides that could be coaxed into a clean stream while everything else was diverted, stripped, or banished. Solvent extraction then separated the nearly identical twins, niobium and tantalum, by exploiting their small but exploitable differences in complex stability. The word fluoride wakes up environmental compliance officers for good reason. Accordingly, modern plants brag, appropriately, about closed loops and reagent recovery. According to company disclosures and process descriptions available in the public domain through 2024 and 2025, the leading Brazilian operation built an industrial habit of recirculating hydrofluoric acid, neutralizing residues, and designing tailings chemistry so that fluoride does not go wandering off into someone else's groundwater. The engineering is not charity, it is the price of running a single operation that supplies most of the world's microalloying habit without provoking regulators or neighbors. Chloride and alkaline alternatives exist and are used where mineralogy plays along. The principle remains the same: dissolve selectively, extract selectively, precipitate selectively. The precipitate of choice is niobium pentoxide, a white to beige powder that sinters like many refractory oxides and behaves as an obliging ferry between ore and metal. To turn that oxide into ferroniobium, you pair it with aluminum in a vigorous aluminothermic reduction. Aluminum has an appetite for oxygen that borders on impolite. When it meets niobium pentoxide under the right conditions, oxygen leaves with aluminum and niobium is left behind, dissolving into iron to form the alloy. The result is a dense ingot that can be crushed and sized into the gravel that rides forklifts and ends up in steel mills' addition bins. The power here is not esoteric metallurgy. It is consistency and cleanliness. If the aluminum is impure or the oxide is contaminated, the consequences show up downstream as inclusions, surface defects, or heat-to-heat variability that makes a rolling schedule feel like roulette. When you control a market, you do so by controlling variance. The niobium route to superconductors is more finicky still. Niobium metal for superconducting radio frequency cavities is made intolerant by design. You reduce the oxide to metal, often via an intermediate halide route in chemical reduction with alkali metals, then you remelt under electron beams in vacuum to cleanse interstitials and tramp elements. The end product is a metal that looks like any other bar until you try to draw it or form it and realize it gives away its secrets only to those who treat it gently. Cavities are spun and welded with almost neurotic cleanliness, they are etched, they are baked, and then, when cooled to around 2 to 4 Kelvin, they become resonant miracles that store electromagnetic energy with quality factors so high you can measure purity with a stopwatch. According to laboratory notes and accelerator facility reports published up to 2025, each tiny impurity, oxygen, hydrogen, nitrogen, has a personality at these temperatures that turns into a real performance penalty. That is why a producer proud of microalloying gravel also advertises, to a completely different clientele, rolled sheets and ingots at a purity level that sounds like an exaggeration until you read the test methods and appreciate what residual resistivity ratio means in practice. Then there are the coils that make the hospital machine hum. Niobium titanium is ductile enough to draw into multifilament wire that can be twisted, insulated, and wound into magnets compactly. Niobium tin is cantankerous by comparison, it offers higher fields, but it is brittle after the reaction heat treatment that forms the superconducting phase. Manufacturers respond with clever routes. The bronze process paints the superconductor into being from copper-tin alloys. The internal tin route hides tin where it can diffuse into niobium under precise thermal budgets. Both require a long, controlled bake to coax the desired compound into uniform filaments without inviting voids or cracks. There is a reason magnet rooms are built like temples to caution. Between the mechanical forces during ramp-up and the stored energy at full field, a defective turn is not a private embarrassment, it is a public event. Niobium's job is to allow all of this to be routine enough to fade into the background of medical care and physics experiments. Back at the mine gate, routine is a fragile thing. Carbonatite deposits weather unevenly. Laterites turn gummy in rainy seasons and crack in the dry. Tailings dams, these words always deserve silence before you say them, must handle slurries with fine particles and residual reagents without creeping toward instability. Operators in Brazil and Canada publish the usual sustainability reports, and independent checks by regulators and third-party audits exist not because corporate virtue is infinite but because the whole world is watching a small group of producers. According to the United States Geological Survey as of 2025, Brazil remains the dominant primary source, with Canada providing a steady secondary stream and other countries proposing projects that cycle through feasibility studies like seasons. A single Brazilian complex at Araxá is the headline act. A Brazilian operation in Goiás and a Canadian mine in Quebec keep the supporting cast real. A handful of African and Australian prospects release news every few quarters and then face the same puzzle. Can you deliver a reagent loop, an offtake agreement, and a capital plan in a market that prefers quiet stability over adventure? That is the niobium paradox. Everyone wants supply security, almost. Nobody wants a price chart that looks like an electrocardiogram. It helps to understand what the steel industry wants to buy. They do not buy niobium, they buy invariants. A pipeline mill needs to know that if they hold finishing temperature and coiling temperature inside a narrow band, the ferrite-bainite balance will fall into the window that satisfies yield strength, tensile strength, elongation, and impact toughness at sub-zero test temperatures. An automotive stamper needs springback within a tolerance their die compensation can handle, not a surprise that wrecks the sequence and smears zinc coatings into a mess. Both of those desires translate upstream into a demand for ferroniobium that behaves the same from January to June. The major Brazilian producer built its business around that singular form of customer service. According to company presentations and analyst notes circulated through 2025, long-term contracts with disciplined volume allocation and application engineering support are not sideshows, they are the main act. Show a mill how to raise strength with a smarter rolling schedule and 1 fewer kilogram of steel per component, and you are not just selling an alloy, you are renting a corner of the customer's process memory. Substitution is the specter in every microalloying conversation. Vanadium and titanium are not imaginary. Heat treat routes that emphasize transformation strengthening without microalloying are not imaginary. If vanadium pricing sits low relative to niobium and a mill's muscle memory is built around vanadium additions, vanadium will win a lot of orders. If a mill knows niobium's rolling schedule's cold and welders like the way the heat-affected zone behaves on niobium-bearing plate, niobium keeps the business. There is also the quiet reality that designers design within their institutional bias. If the finite element models assume the strain hardening curve you get from niobium-bearing material and production has been living in that playground for years, the switching costs are not just the price of a bag of alloy, they are the price of unwinding a comfortable process control envelope. Niobium's calm price posture, again, according to public market commentary and the United States Geological Survey's consistent summaries, has been a strategy to convert that bias into a moat. Do not give the customer a reason to call the vanadium rep. The case study version of all this looks like a straight line on a map with a lot of process hiding under it. Start at a lateritic hill in Minas Gerais, weathered from a carbonatite body intruded deep in geologic time. Drill, model, and design a pit whose benches carve through clay-rich overburden into ore layers that are friendly to the concentrator. Crush and grind with enough finesse to liberate pyrochlore without making slimes that float like ghosts. Float with collectors developed through scar tissue and bench experiments until you hit a concentrate that feeds a chemical plant with predictable behavior. Leach in a closed fluoride loop with a smell that makes newcomers take a step back. Extract and strip through solvent stages that look like a chemistry teacher's fever dream scaled up by a factor of 1,000. Precipitate niobium pentoxide that filters and calcines into a consistent powder. Reduce with aluminum to make ferroniobium. Size, bag, and ship. Somewhere in Alberta or in the Permian Basin or in the North Sea, a plate mill turns that alloy into a property sheet. A pipe mill turns that plate into helically welded pipe. A contractor bends that pipe on a cold morning and welds in a wind that keeps trying to steal the shielding gas. The inspector signs off because the microstructure in the heat-affected zone behaved. A year later, a smart pig glides through the pipeline listening for defects and finds mostly the sound of laminar flow. You could tell the same story for a car frame or a ship deck, and the plot would be identical, a thin line from a carbonatite hill to a world that kept its promise. Not every plot resolves neatly. Consider a North American project that has promised, since the mid-2010s, to deliver a domestic source of niobium along with scandium and titanium. Company filings across those years read like a chronicle of feasibility studies, pilot plant tweaks, offtake negotiations, and financing plans that walk right to the edge of reality and then pause. The underlying geology is plausible, the flow sheet is within the realm of existing chemistry, the market would welcome a new, friendly jurisdiction source. And yet, turning a plausible project into a capital stack that clears and a supply chain that trusts you is harder than a slide deck makes it look. The lesson is not that niobium is impossible outside Brazil and Canada. The lesson is that a quiet market punishes delays because customers cannot wait forever to lock in their rolling schedules and alloy bins. Meanwhile, a Tanzanian niobium prospect with hopeful feasibility numbers in the mid-2010s discovered that currency gyrations, permitting complexity, and capital discipline from lenders can turn an elegant spreadsheet into a long pause. These are not cautionary tales about geology, they are reminders that microalloying is a business of trust. Talking of trust, let us visit the new frontier everyone wants to believe in, batteries. Niobium pentoxide and niobium-rich complex oxides have appeared in research papers and company roadmaps as anode materials that trade energy density for charging violence. The promise is intoxicating for buses, delivery fleets, and grid-adjacent storage, charge in minutes, live for tens of thousands of cycles, shrug off abuse. The physics is modestly straightforward. Niobium-based oxides can host lithium ions in open crystal frameworks that let ions move without squeezing the lattice like a balloon, which cuts down on the mechanical fatigue that murders graphite and silicon at high rates. According to conference presentations and pre-commercial announcements through 2024 and 2025, pilot cells with niobium-based anodes deliver power performance that looks like science fiction to anyone raised on 8-hour charges. The caveat is classic materials engineering. The crystals are heavy, the specific capacity is not thrilling, and the bills of materials must travel from a mine that already serves steel to a cell factory that hates surprises. If a battery maker can live with lower kilowatt-hours per kilogram in return for reliability and speed, the match might work. If passenger cars keep chasing ever longer ranges, niobium's battery career may remain a specialist. Recycling is where romantic narratives go to be measured. In steel, niobium is recycled because steel is recycled, not because anyone sought scrap for niobium content. You melt what comes in, you analyze, and then you correct with microalloy additions to hit the specification. The tiny mass fraction of niobium per ton makes targeted recovery from scrap uneconomic. It is there, you just do not chase it. In the high-purity world, retired superconducting magnets and cavities are occasionally harvested for their metal content, but volumes are small and pathways are bespoke. A circular economy built on niobium would be a circular economy built on the hosts that carry niobium, the steels and the devices. That is not nothing. It means that a secondary steel grows as a share of the metallic economy. Niobium atoms enjoy second and third lives. It also means that primary niobium remains the way you meet tomorrow's specification sheets with tight tolerances. If you want an image to carry into the rest of this lecture, keep the pocket scale contrast in mind. Upstream, a few benches on a few pits dominate the world supply. Downstream, the alloy is sprinkled across millions of tons of steel that become ordinary things: pipe, plate, beams, forgings, stampings. Control sits upstream because that is where consistency is manufactured. Value is realized downstream where a mill's first time through rate and a world crew's lack of complaints are counted as profit. The quiet stability of prices and volumes is not a market failure. It is a market design where one company decided, decades ago, that the best way to make niobium essential was to make it dull. According to the United States Geological Survey's steady framing in its 2025 summaries, that design has held. Engineers rely on it. Governments eye it warily. And a handful of project developers keep trying to thread the needle between credible and funded in a niche that rewards patience more than bravado. The practical implications are easy to miss because they wear hard hats. If you specify a bridge deck plate today and you want it to stay tough in winter and not drive the welding team to despair, you write down a strength level, an impact test temperature, and a requirement for good formability. Somewhere between your pen and the plate rolling mill, a decision is made: a pinch of niobium, a pinch of vanadium, maybe a little titanium to control nitrogen, and a rolling schedule that has been proven in the mill's sleep. If the mill's preferred path is niobium, your bridge gets niobium. If the mill's preferred path is vanadium, it gets vanadium. You will not be told. You will not need to be told. You will drive across that bridge in February and never think about a carbonatite in Minas Gerais or a solvent extraction bank in a plant with floor drains labeled like airliner checklists. That is the mark of a material that has entered the bloodstream of modern engineering. It works, it behaves, it frees you to think about other parts of the design. The spotlight does not follow it, the savings do. You can tell a material has matured when the arguments about it become arguments about time. Not, what is it, not, does it work, but, how soon does it start, how long does it last, how much faster can we push the line without inviting gremlins? Niobium lives in that adult world. Rolling schedules are tuned to minutes, weld procedures are tuned to degrees Celsius, magnet makers count oven hours like vintners count growing days. This is not a metal that tolerates vibes. It tolerates process windows. Start with the most bureaucratic window in the steel universe, the grates for line pipe that move oil and gas across continents. The American Petroleum Institute does not love surprises. Those great names that sound like license plates are really promises about yield strength and toughness measured at sub-zero temperatures, promises that only land if the microstructure lands. According to line pipe specifications widely used through August 2025, mills lock in a dance of finishing temperatures and coiling temperatures that repeatedly delivers ferrite and bainite in a morphology that shrugs at notch toughness tests. The reason niobium is the quiet hero of this routine is that it extends the safe zone. It lets you hit target strength without pushing carbon high enough to make welders pay for it, and it narrows the variance so the same schedule works in January and in June. There is a reason pipeline owners will pay for boring. Boring saves dig-ups. The same time obsession sneaks into automotive steel, only here the villains have different names. A stamping press is unforgiving. If your springback is off, you do not get a philosophical discussion, you get a bin of parts that look like they are impersonating the right shape. Niobium helps by sharpening the grain size distribution and by feeding a controlled rain of niobium carbide and niobium nitride particles during cooling that leave the steel both strong and tame. Press hardening for side impact beams and pillars forces another kind of timing. You austenitize, you quench, you form, and if the steel's response curve slides around from heat to heat, your dies pay the price. According to application engineers who publish case notes for this niche, small doses of niobium keep the curve where the tooling people expect it, which is a fancy way of saying the plant manager does not walk over to your desk with that look. Once you notice the time dimension, you see it everywhere in the niobium story. In nickel-based superalloys, the famous ordered precipitate that uses niobium as an anchor is not just a phase, it is a calendar. You heat, you hold, you cool, and the precipitate distribution either shows up on schedule or it does not. When it does, turbine disks laugh at creep for years. When it does not, inspection finds hints of future misbehavior, and future misbehavior is not a viable business model at takeoff. The role of niobium here is subtle. It is not the loudest alloying element in the recipe, but it tunes the precipitate lattice in a way that buys strength without making the material unforgeable. That is the kind of compromise designers love, a little more field margin without a lot more manufacturing drama. Superconductors make the timing point with a hammer. The superconductor made from niobium and titanium is ductile enough to draw into thousands of filaments. The one made from niobium and tin becomes brittle after a carefully timed heat treatment coaxes the compound into existence. Magnet makers therefore plan the entire life of the wire around that thermal reality. You wind early, you react late, and you baby the coil forever after. According to accelerator and magnet facility documentation available through 2025, even small deviations in the reaction schedule create weak links where current crowds and quenches begin. The material choice is not a trophy for physicists, it is an engineering decision about which timeline you can keep. The upstream end of niobium's supply chain has its own calendar and its own habit of punishing anyone who ignores it. Carbonatite-hosted ore bodies are patient geologic features, but their weathered caps are seasonally moody. Laterites swell and slump with rainfall. Clay fractions play tricks on flotation. Operators in Minas Gerais learned long ago that you do not force a mine to be consistent, you force your plant to make the mine's inconsistency irrelevant. That is why the public descriptions of the leading Brazilian operation read like a meditation on closed loops. Hydrofluoric acid does not wander off. Water recirculates until it squeaks. Tailings are blended and thickened so dam engineers sleep at night. According to company sustainability reports and Brazilian regulatory disclosures through June 2025, the reagent recovery systems are engineered as if reputation lived or died on them, which in a concentrated market is exactly right. A single headline can reset policy in a dozen countries in a week. When most of the world's ferronibium is born in one industrial complex, you do not tempt fate. Concentration this high creates the strangest power dynamic in modern materials. The market is small, the supplier is large, the customers are innumerable. It should be a setting for abuse. Instead, it is a setting for standards. According to the United States Geological Survey in 2025, Brazil supplies the majority of primary niobium, Canada contributes a steady portion. Other jurisdictions promise and then negotiate with geology, capital, and permitting. The leading Brazilian producer prices mostly by quiet contract rather than public spectacle, offers application engineering that melts into the customer's process control, and treats variance as an existential threat. The result is that designers keep specifying niobium because the cost is predictable and the performance is automatic. Stability is a moat. It is also a responsibility, because if that single river stumbles, designers will reroute around it with vanadium or with heat treat tricks that try to dodge microalloying altogether. Substitution thresholds are not theory. They are phone calls. Those phone calls have a tone. When vanadium is cheap and abundant, its salespeople arrive with curves showing precipitation kinetics that can deliver the same strength class in certain sections and rolling conditions. When titanium wants to be helpful, it does so by tying up nitrogen and carbon in ways that protect weld heat-affected zones from grain growth. If you run a mill that knows the niobium schedules by heart, changing those levers is not simply swapping a bag in the addition bin. It is changing your cooling temperatures, your weld procedures, your die compensation, and your inspection criteria for the next year. According to steelmakers who have publicly discussed these choices in the past decade, the path dependence is real. You do what you are good at until cost or availability forces a rewrite, and then you rewrite only as far as you must. This is why niobium's oddly calm pricing posture across many years matters more than press releases. It holds the line on inertia. It keeps the spreadsheet from lighting up an alternative. Policy notices, too, prefer inertia. Niobium sits on the United States government's critical minerals list as of 2025, alongside the European Union's supply risk watch lists. Yet you do not see dramatic stockpile purchases or export controls targeted at ferroniobium. You see quieter things, memoranda of understanding with Canadian and Brazilian counterparts, grants for process research on environmentally gentler leaching routes, pilot money for niobium-bearing anodes that might create enough new demand to justify new sources, feasibility support for domestic projects that will not get built on vibes alone. What you do not see is panic, because the supplier who matters most has built an identity around not inspiring panic. Every once in a while a rumor of maintenance outages or expansion slippage will nudge buyers to look at alternatives. Then the maintenance finishes, volumes resume, and spreadsheets drift back to their usual lines. There is a detail about the downstream that deserves more fame than it gets. Niobium is the rare critical material whose major host, steel, is itself the backbone of recycling. According to steel industry statistics through 2025, a large and growing fraction of steel production in many regions starts as scrap. Those tons carry their microalloy ghosts with them. The niobium rides along into the melt, undistinguished and unbothered, and then the melt is corrected with fresh microalloy additions to hit the specification. Purists will say this is not real niobium recycling because you cannot economically sort scrap by niobium content and recover the element. Realists will say it is exactly the kind of circularity that works. The base host circulates, and the microalloy is replenished in small doses. Both are right. The constraint that remains is simple arithmetic. If total steel tonnage grows, primary niobium demand grows, even as scrap rates rise. You cannot downalloy your way out of geometry. The flashy exception to the steel eats almost all of it rule is batteries, partly because the chemistry is genuinely interesting and partly because companies love to talk about anything with the word battery in it. Niobium pentoxide can be turned into a menagerie of complex oxides with tunnels and layers that let lithium ions move fast without destroying the host structure. Titanium niobium oxide is the example most often cited in public announcements because it pairs two abundant elements and delivers blistering charge rates, albeit with modest energy density. Niobium tungsten oxide has shown up in journals for its open channels and friendly diffusion constants. According to company roadmaps and academic papers presented up to August 2025, pilot cells using these anodes can charge in minutes and live for what feels like geological time compared to passenger car batteries, with safety margins that make bus depots and industrial fleets breathe easier. The cost question is still a grown-up. The oxides are heavy, the specific capacity will not win a beauty pageant, and supply chains must connect a mine that speaks the language of ferroniobium to factories that speak the language of pouch cells and yield loss. If any of these anodes graduate into commercial volumes, they will likely do so in niches where power beats energy, Heavy vehicles that park under chargers, storage that cycles hard, machines that hate downtime more than they love range. Company pivots are catnip for the trade press, but in niobium they tend to be technocratic rather than theatrical. The leading Brazilian producer has spent years funding battery research partnerships in Japan, Europe, and Brazil, has funded graphene-adjacent tinkering, has marketed niobium-bearing additives for a grab bag of uses from coatings to cement, and has courted automakers with the dry confidence of a supplier who already has a foot in their chassis. According to company filings and conference presentations through 2025, the pitch is not reinvent the world. It is take 5% weight out of this steel component without changing your tooling, or shave 15 minutes off your charge time without scaring your safety team. Meanwhile, in Quebec, a mine that has changed owners has explored expansions and value-added products beyond ferroniobium, including higher purity oxides that feed into aerospace and electronics. These moves are not headline fireworks. They are a steady attempt to make niobium slightly more present in slightly more corners of industry so that dependence on any single demand channel does not become a single point of failure. We should talk about a fiasco, if only to make clear that this is not a fairy tale. The domestic North American project that promised niobium along with scandium and titanium learned, repeatedly, that a credible flow sheet, a credible ore body, and enthusiastic customers are necessary but not sufficient. Financing for chemical plants that handle hydrofluoric acid is difficult under the best of circumstances. Securing offtakes that bankers accept as bankable rather than aspirational is harder still. Building in a county that has never hosted such a plant demands a diplomacy that few teams possess. According to a decade of public filings up through 2025, the project spent years oscillating between feasibility study revisions and funding announcements that withered under scrutiny. The geology did not betray them, capital discipline did. Across the ocean, a niobium deposit in East Africa with respectable numbers on paper discovered that exchange rate swings, shifting regulatory expectations, and global risk appetites can turn an elegant internal rate of return into a call us later. Neither story should be read as a verdict on the metal. They are verdicts on execution in a market that does not pay premium for adventure. Niobium's environmental ledger is better than the sulfur and smoke caricature of metallurgy, but it is still a ledger. Weathered carbonatites invite careful water management, because fine particles travel like rumors and clays love to hold water where you wish they would not. Fluoride chemistry, even in heroic closed loops, sets a high bar for containment and for post-closure care. According to Brazilian Environmental Agency documents and independent audits cited through 2025, modern plants meet those bars with redundant systems and obsessive monitoring, and the leading producer has spent real money on tailings dam design that follows international best practice rather than local minimums. That is good news. It is also a reminder that materials we call critical are critical not only because of geopolitics but because of the engineering required to make them safe. If the market truly diversifies, that safety culture has to travel with the chemistry into every new jurisdiction that wants a piece of the business. There is a quieter coupling we should not ignore, the way one critical material's constraints amplify in others. Magnetic resonance imaging magnets rely on niobium and titanium wire and on liquid helium. When helium markets tighten, hospitals notice, and they notice in ways that can ripple back into magnet procurement, service schedules, and upgrade plans. According to hospital procurement reports and service bulletins over the past several years, helium conservation technology has improved, but the feedstock is still a molecule sourced from a handful of fields. The irony is almost comic in a dark way. The metal that makes a life-saving magnet possible is abundant enough in chemistry and geology to be calm and reliable, and the cryogenic fluid that lets that magnet work is the one that sends the spreadsheet into italics. The lesson is not to panic about helium, it is to remember that supply security is a chain, and chains break at their weakest link, not their most famous one. This chain metaphor also explains why niobium's value creation is so dispersed. The mine makes money. The chemical plant makes a little more. The aluminothermic reduction and alloy sizing make the product recognizably useful. But the real value is realized where variance dies, in mills that enjoy a first-time through rate that keeps overtime off the schedule, in welds that do not spawn repairs, in stampings that match their dies the first time, in magnets that ramp without drama, in turbines that keep their promise at heat. The material is an enabler. It shows up as risk removed. In a world that fetishizes breakthrough headlines, niobium earns its keep the way an experienced foreman does, not by grandstanding, but by preventing 1,000 small errors that would have cost you days. If you want to see control in action, imagine a midstream steel plant that has gotten very good at niobium. The operators speak in finishing temperatures the way a baker speaks in proof times. They know which heats will behave because the lab numbers came back inside a fingerprint pattern they recognize. The plant's digital systems nudge recipes within narrow bands. The crew walks past the addition bins and does not think twice about the gravel of the Niobium because every bag behaves. The mill's customer wants a new strength level with the same forming behavior and the same galvanizing response. The Niobium team tweaks solutioning and coiling temperatures, shaves carbon by a sliver, and holds the line on weld toughness. When the results land, the customer thinks the mill grew smarter. The mill knows the metal helped. Everyone gets to keep their illusions, and the invoice gets paid. Zoom back out to the geology map and you see how strange the whole story is. A handful of carbonatite intrusions, some weathered into laterites, in 2 friendly jurisdictions, control an alloy addition that quietly sets the tone for pipelines, cars, ships, buildings, and medical machines. According to reserve and resource summaries compiled by the United States Geological Survey in 2025, identified niobium resources exist on several continents, but only a few have chemistry, infrastructure, and social license arranged in a way that turns dirt into contracts. This is the political economy of boring excellence. The countries that host those mines enjoy a quiet leverage not because they can starve the world, but because they can keep it fed without drama. Everybody else tries to stand up a project or two, partly for security, partly to create an alternative should the river ever dry. Most of those attempts will not make it to production. The ones that do will join a club that prefers soft-spoken competence over marketing. There is one more timing truth to leave hanging in the air, because it will govern the next decade of niobium more than any single press release. New mines and new chemical plants do not appear when you clap. They appear when 1,000 small, boring, difficult pieces align, drill results that remain consistent, metallurgical test work that behaves at scale, reagent loops that close without surprise, offtake agreements written by people who will still hold their jobs in 5 years, communities that see their lives getting better, not just their hills getting shorter. According to every feasibility study that ever mattered, that alignment takes years. If niobium demand grows even modestly, because steel tonnage rises, because bus fleets want violent charging, because a few more laboratories want higher fields, the right time to start the next plant is yesterday. The right time to start teaching a new mill how to roll niobium-bearing steel is today. The right time to proof your tailings design against weather nobody has seen in living memory is also today. Materials that buy you time deserve the courtesy of being given time in return. Start with a forklift and a bag that looks like feed for a mythical animal. The tag says ferroniobium. The bag weighs a metric ton, the granules inside are dull and gravelly, the paperwork is immaculate because steel mills like their surprises to happen on someone else's shift. A buyer has not purchased a metal so much as a promise, add so many kilograms of this to so many tons of melt, and the rolling schedule will hit its marks. That promise has a price, but more to the point, it has a personality. The price barely twitches year to year, the personality is predictability with a stubborn streak. That is not how commodities are supposed to behave. That is how a quiet oligopoly behaves when it would rather be a utility. Niobium's pricing is famously uneventful, and that is a strategic choice rather than a trick of fate. According to the United States Geological Survey in 2025, the majority of primary supply still comes from Brazil, with Canada as a steady second and a dribble from elsewhere. The dominant Brazilian producer has long favored multi-year contracts, application engineering support, and a studied disdain for spectacle. The theory is simple and has worked for decades. The more predictable niobium is, the more often designers will specify it, the more often designers specify it, the harder it is for alternatives to displace it on price alone. You do not go hunting for vanadium substitutions if your mill, your welding procedures, and your field crews already trust the niobium path and the invoice never makes procurement sweat through a shirt. If you trace that contract down the value chain, you discover how much of niobium's value is really variance management in disguise. The alloy arrives in bags or drums, usually in a composition around 60% niobium by weight with iron as the balance and impurities carefully policed. Mills meter it into the melt late, just ahead of tundish and mold, because the whole point is to have niobium sitting in solid solution in austenite when the real work begins. The addition practice is a ritual because hitting solution content without overshooting is the difference between a sweet spot precipitation of niobium carbide and niobium nitride during cooling and a cranky microstructure that refuses to land inside the property window. The bag does not look like leverage. In practice it is process control poured from a forklift. Even within steel, the niobium portfolio is broader than the pipeline clichés. Structural plate mills use it to raise yield strength without nailing carbon upward. Rebar producers use it to tune strength and weldability for seismic zones. Shipyards translate it into deck plate that keeps toughness at lower temperatures without building hulls that weigh like regret. Stainless makers use niobium as a stabilizer in grades intended to resist intergranular corrosion after welding. The stabilizer role is underappreciated. Niobium has a talent for tying up carbon in carbides that do not betray grain boundaries later, which gives petrochemical piping and exhaust components a longer, quieter life. Designers often think strength, but maintenance engineers hear less drama at welds after 5 winters. Nickel-based superalloys tell a complementary story. If you peek into the microstructure of a workhorse alloy for turbine discs, you find a fine dispersion of ordered precipitates, some of which take advantage of niobium's atomic size and electron count to strengthen without making the material unforgeable. You achieve that distribution with schedules measured in hours, not instincts, solutioning, aging, sometimes a double H to balance creep resistance and tensile behavior. Niobium is not the headline ingredient in these recipes. It is the tuning peg. It nudges the lattice parameters of the strengthening phases just enough to buy extra capability at temperatures where aluminum and titanium-driven strengthening alone would not carry the load. The extra capability turns into engine designers raising turbine inlet temperatures by a nudge and maintenance departments sleeping slightly better. Superconductivity is the far end of niobium's personality, and it shares a family resemblance to the steel story. The metal acts as a ruthless editor of variance. Niobium and titanium wire is drawn into thousands of filaments, coupled with copper for stabilization, and wound into magnets that make magnetic resonance imaging possible. Niobium and tin pushes the field higher but punishes sloppiness. You wind first, heat treat later, and once you have formed the superconducting compound, you handle the coil like a relic in a museum. The performance metrics, critical current density, upper critical field, not arcana, they are operational limits. According to accelerator laboratories and magnet makers whose reports remained steady through 2025, tiny deviations in reaction time and temperature create weak links and premature quenches. Niobium's job is to allow industrial practice to repeatedly land on a narrow plateau where superconductivity is both high-performing and boringly reliable. Upstream, boring reliability does not come cheap. Carbonatite-hosted ore bodies hand you a mixed bag of mineralogy. Weathered caps can be clay-rich and moody with the seasons. Pyrochlore liberation wants a grind that cuts cleanly without producing slimes that stick to froth. Flotation needs collectors tuned to chemistry that changes bench by bench. The Brazilian complex that anchors the market leans on closed-loop chemistry to keep fluoride where it belongs. According to company sustainability reports and Brazilian regulatory filings through June 2025, hydrofluoric acid is recirculated, water is recycled until it behaves, residues are neutralized with an engineer's paranoia, and tailings dams are designed to international standards rather than local minimums. This is not green theater. It is how you earn permission from the world to run a single facility that supplies a majority share of the microalloying habit without becoming a household name for the wrong reason. The Canadian operation is a useful contrast. The geology is similar enough to be familiarly recognizable but different enough to force changes in flowsheet details. Ownership has shifted over the years, expansions have been studied and shelved and studied again, and value-added products have been explored as ways to climb higher in the price stack than plain ferronium. That resilience matters. Even if Brazil never stumbles, having a second pole of supply keeps the market's blood pressure down and gives policymakers options that are not press releases. According to the United States Geological Survey's consistent summaries through 2025, the Canadian mine's steady output is more important than its market share suggests for precisely that reason. It anchors optionality. The idea of optionality brings us to geopolitics, which in niobium is as soft-spoken as the metal itself. You will find niobium on critical minerals lists in Washington and Brussels, and you will find polite communiques between Brazil, Canada, and the countries that buy most of the ferronium. You do not find export controls or public saber-rattling. You find memoranda of understanding, research grants for less hazardous leach routes, and feasibility stage nudges for new projects in friendly jurisdictions. The most significant geopolitical maneuver in recent memory was not a sanction or a tariff. It was the leading Brazilian producer selling minority stakes to a consortium of major Asian steelmakers in the early 2010s, aligning customer incentives with supplier stability. According to company announcements from that era, the logic was explicit: bind buyers into the long game so that nobody is tempted to treat their owl edition like a spot commodity when sentiment swings. Substitution is the other geopolitical valve, and it is controlled not by ministries but by engineers with calendars. Vanadium can deliver similar strength classes in many sections, especially when carbon can be pushed a touch higher without wrecking weldability. Titanium can do useful housekeeping by tying up nitrogen and carbon. Heat treat strategies that de-emphasize microalloying can sometimes skate around the need altogether. But these are not universal substitutions. They are case-by-case rewrites of rolling schedules, die compensation, and weld procedures. The inertia of competence is a moat. A mill that knows niobium's thermomechanical window by heart and a field crew that trusts the heat-affected zone behavior are not in a hurry to rewrite their muscle memory in exchange for a theoretical cost advantage. They will rewrite when a supply scare forces it or when a customer's design target moves far enough to justify the experiments. Hydrogen pipelines are a good example of design targets on the move. Transporting hydrogen at pressure turns fracture toughness from a line item into a liturgy. Microstructures that shrug at methane can sulk in the presence of hydrogen. Early work by steelmakers suggests that low-carbon microalloyed steels strengthened with niobium, sometimes nudged with a breath of nickel, can deliver the combination of strength and toughness you want for hydrogen service without turning welding into a casino. The physics is the same as ever: grain size control, precipitation discipline, transformation pathways, but the tolerances tighten because hydrogen changes the rules just enough to make old intuition suspect. If hydrogen infrastructure grows in the 2030s, this is one of those quiet domains where niobium earns keep by keeping people out of the headlines. Batteries are the opposite, a domain that loves headlines. Niobium pentoxide can be coaxed into complex oxides with crystal frameworks friendly to rapid lithium insertion and extraction. Titanium. Niobium oxide and niobium tungsten oxide are the poster children because they are stable, conductive enough when doctored properly, and amenable to violent charging. According to company roadmaps and academic papers presented up to August 2025, pilot cells with niobium-based anodes reliably hit charge times measured in minutes, cycle counts in the many thousands, and safety behavior that makes fleet operators relax. The trade is energy density. These crystals are heavy and do not store as many lithium ions per gram as graphite or silicon. That is fine for buses that park, for industrial equipment that hates downtime, and for grid storage that lives on fast turnarounds. It is less fine for passenger cars chasing range number theatre. If this niche grows, it will not replace the steel share. It will add a new pillar that justifies more mines or expansions with chemistry that already exists in the niobium world. Additive manufacturing is another place where niobium prowls around the edges, usually as a deliberate addition to steels where resistance and toughness need to coexist in shapes that would have been awkward to machine traditionally. Niobium's carbide-forming habit lets designers sprinkle hard particles through a matrix without making the whole part brittle, a trick that becomes more interesting when you can place those particles where geometry and load demand. Stainless grades stabilized with niobium also play friendlier with lasers and electron beams than their unstabilized cousins, because the stabilizer lessens the risk of sensitization after thermal cycling. Nobody is printing aircraft carriers out of niobium-bearing steel. Plenty of people are printing inserts, wear plates, and intricate heat exchanger geometries where local strength and corrosion behavior pay rent. On the environmental ledger, niobium benefits from the company it keeps. Steel is the arch recyclable material. The presence of niobium does not change that. The microalloy rides through electric arc furnaces and basic oxygen furnaces without fanfare, and mills correct alloy content on the fly to hit each heat's target. Purists will point out that this is not recycling niobium, in the sense of pulling it back out and reselling it as niobium. It is simply recycling steel that happens to contain niobium. Realists will counter that this is the kind of circularity that scales. You do not need to detect parts per million of a microalloy atom in a shred pile to get the environmental benefit of a steel loop that shortens all trains. At the high purity end, superconducting hardware is technically recyclable into niobium feedstock, but volumes are small and the logistics are bespoke. The honest answer is that primary niobium remains the way we meet growth. Secondary flows soften the edges at the steel scale. Tailings and reagents remain the adult problems upstream. Laterites behave badly when rain patterns change. Clays hold water when you want them to drain and drain when you want them to hold. Fluoride is a tool you do not allow to wander. According to Brazilian Environmental Agency documents and independent technical audits through 2025, the major operations have adopted thickened tailings, redundant monitoring, and reagent recovery systems designed to survive human error and bad weather. The moral is not that niobium is clean by nature. It is that niobium is as clean as its flowsheet discipline, and flowsheet discipline is as good as the culture of the teams who run it. In a concentrated market, culture is risk management. There is a quieter cultural piece downstream, and it is digital. Modern mills run on models. Finishing temperatures, coiling temperatures, reduction schedules, cooling rates, these are not tribal secrets passed by a nod, they are digital recipes with narrow tolerances and feedback loops. Niobium fits that world because its effect is predictable when the calendar is kept. Process control systems like materials that let them hit a target without backtracking. In return, the metal benefits from customers who can feel and measure the value of variance reduction, not just the headline numbers on a tensile test. You can see this dance in how quickly new grades are qualified, pilot coils run, press shops measure springback, weld labs abuse heat-affected zones, and the models refine. Every time the loop closes with boring results, the moat around niobium gets a little wider. Trade flows are humbler but worth noticing. Ferroniobium travels well. It writes ships in big bags, sits in warehouses without fretting, and survives customs paperwork because its classification is straightforward. The customers are diffuse, hundreds of steel mills and foundries across 5 continents, and the touchpoints are simple: delivery on time, composition on spec, granule size suitable for addition practice, paperwork that lets a lab sign off without a phone call. The biggest logistical risk is mundanely modern: congestion in ports, hiccups in container availability, and the occasional line closure that forces bagged product into bulk and back again. When people in the niobium world say they prefer boring, this is what they mean: the less the logistics manager has to invent, the more the rolling mill can run. The textbook, Fiasco with Lessons, is not a fireworks show so much as a slow-motion learning curve. A North American project that promised niobium alongside scandium and titanium ticked geological and metallurgical boxes on paper but discovered that closing a capital stack for a chemical plant that handles hydrofluoric acid is an endurance sport. Bankers want offtakes that read like bonds, not love letters. Communities want confidence born of experience, not artists' impressions. Company filings over the past decade read like a diary of near misses, credible or plausible flow sheet, customers who would sign if a plant existed, financiers who would finance if those customers signed first. Across the ocean, a Tanzanian carbonatite with good-looking numbers discovered the arithmetic of risk premiums and exchange rates. Neither story indicts niobium. Both stories remind us that in a market designed for calm, the penalty for being late is that customers quietly solve their problems another way and do not come back. Future growth, to the extent it happens, will not arrive as a single headline. It will arrive as a collection of nudges. A few pipeline projects designed around hydrogen rather than methane. A few automakers leaning harder on niobium-stabilized stainless in hot-end exhaust paths for life extension under tougher emissions regimes. A few mining trucks and buses buying niobium-based anode cells because downtime is the enemy and range is a nice-to-have. A few foundries adding niobium to wear-resistant overlays in parts that were previously consumables. None of these will individually move mountains. Together they justify incremental expansions and maybe, if the stars align and bankers regain their courage, 1 or 2 new entrants with modern reagent loops and tailings designed for the weather of the 2030s rather than the weather of the 1980s. And if you want one number to hold in your head the next time you see a pipeline bend in winter or step into a hospital where a magnet was behind a wall, use around 1. A few hundred grams of niobium per metric ton of steel. That is the scale of the whisper. Not a revolution by the truckload, but a handful that turns a process window into a process habit and a process habit into infrastructure that behaves. In a century addicted to spectacle, that is a quietly subversive way to matter. Picture a bus depot at dawn in January. A mechanic with a coffee mug and a stopwatch watches an articulated electric bus pull in hot after a brutal, pre-sunrise run. A stack of chargers coughs out a hum like a choir clearing its throat. 10 minutes later the bus is ready to turn around again. The fleet manager does not care about crystal structures or precipitation kinetics. The only questions are whether the charging bay will behave at this speed and whether the cells will still be happy after 60,000 cycles. In one of those packs there is a new anode chemistry, niobium-rich oxides that trade raw energy for a kind of charging ferocity, and the stopwatch says the trade is worth it. That one test, repeated 100 times through the winter, rolls up into a procurement choice. It is not a revolution. It is one more place niobium turns a process window into a process habit. Now follow the habit upstream until you hit rock. The modern niobium map looks deceptively simple when you sketch it on a whiteboard. A carbonatite intrusion in miners' Juraris weathered into laterite and quarried with discipline. A sister operation in Goyas that mines and concentrates a similar ore family and turns it into alloy under the same unforgiving standards. A mine near Saguenay in Quebec that sends underground trucks along quiet drifts and feeds a concentrator that has been tuned like a metronome. According to the United States Geological Survey in June 2025, those operations together supply most of what steel mills call ferroniobium and most of what the world casually calls niobium. That concentration is not an accident, It is the endpoint of 1,000 engineering choices that reward companies able to keep reagent loops closed, tailings stable, and heat-to-heat variance down to the width of a spreadsheet column. The rest of the map is dotted with possibilities. An Australian polymetallic project that wants to make niobium alongside zirconium, hafnium, and rare earths. An American project in Nebraska that has promised, through successive feasibility studies, to deliver niobium with scandium and titanium. An East African carbonatite with pilot plant dreams that keeps pausing for the realities of capital and governance. A Russian rare earth deposit with niobium that looks compelling in diagrams and complicated in geopolitics. A Chinese ecosystem that squeezes small streams of niobium out of polymetallic flows yet still prefers to import ferroneobium when it wants volume and reliability. On paper these dots look like easy diversification. In practice, each one must redevelop the culture and the chemistry that the incumbents have already made boring. Boring is the point. The dominant Brazilian producer turned an alloy addition into an industrial utility by making 3 choices decades ago and then refusing to get cute. Price by contract, not by circus. Invest in application engineering so customers solve problems with you rather than around you. Treat variance as the only unforgivable sin. That is why this story reads oddly for a critical material. You do not get the cobalt boom-bust drama. You do not get the vanadium yo-yo where rebar standards and Chinese inventory cycles turn a price chart into a cardiogram. You get a slope that leans gently up with steel tonnage and a thrum of steady bags moving from ships to mills. When the company sold minority stakes to a consortium of Asian steelmakers in the early 2010s, it was not a liquidity event, it was a social contract. Bind big buyers into the long game, make everyone allergic to surprises, and the metal will find its way into more specifications with less debate. From that altitude, you can watch substitutions circling like patient hawks. Vanadium wants to move in when it can add strength without breaking welding procedures. Titanium wants to tidy up nitrogen and carbon so stainless grades stay sweet after welding. Higher temperature superconductors want to outfield magnets built with niobium and tin. Heat treat recipes want to do an end run around microalloying altogether. Engineers are not ideologues, they are opportunists with calendars. If the price of vanadium sits in the basement for a stretch and a mill's muscle memory can support a switch, a vanadium route becomes attractive for certain sections. If a magnet program needs fields that niobium and tin cannot give without misery, a ceramic tape with a frightening price tag and a touchy mechanical personality begins to look like a necessary vice. But these are never universal fixes. They are specific edits to specific schedules with specific consequences for forming, welding, inspection, and service life. That is why niobium's calm demeanor has strategic value. It does not make substitution impossible. It makes substitution an effort, which means it only happens when there is a real reason. Hydrogen service is the kind of reason that can force a rewrite. Moving hydrogen at pressure asks more of steel than moving methane does. Fracture mechanics gains a vowel, becomes a liturgy, and the heat-affected zone is no place for experiments. The current playbook points toward low carbon. Microalloyed steels strengthened with niobium, sometimes nudged with a breath of nickel, to hedge against embrittlement. The physics is familiar. Control austenite, precipitate niobium carbide and niobium nitride on schedule, do not give grains an opportunity to grow in the heat-affected zone. But the tolerances tighten because hydrogen is uncharitable. The real work will happen in full-scale burst tests, weld procedure qualifications written like case law, and in the slow, boring accumulation of service data. If a hydrogen economy is truly a thing in the 2030s, niobium will have earned its way there 1 mil test bar at a time. Superconductivity lives on a different calendar, and niobium sits at the center of it with the stubborn practicality of a craftsman. Magnets for magnetic resonance imaging and for accelerators are built out of wire made from niobium and titanium that behaves in factories, and out of wire made from niobium and tin that behaves only if technicians treat it like spun glass after a carefully scripted reaction bake. Hospitals do not budget for the latest phase diagram, they budget for magnets that ramp and hold without drama while helium behaves like a responsible adult. Research labs push fields higher and higher and will happily fight ceramic tapes and brittle bends in return for an extra Tesla. The wire makers succeed by rehearsing to within an hour and a degree Celsius, then doing the same thing for 10 years. That is the kind of stability niobium rewards. It does not win because it is the wildest physics. It wins because it lets complex machines be boring. The environmental ledger is where boring must be earned. Weathered carbonatites produce slurries that love to move when they should sit, and clays that love to sit when they should move. Hydrofluoric acid is a tool that requires monastic discipline. The leading operations know this and publish like people who understand that their social license is indexed to their ability to keep fluoride on site, water recirculating at high percentages, and tailings engineered to standards that assume the climate is changing faster than tradition is comfortable admitting. It is not green theater, it is operating reality in a market where a single headline can ricochet through national stockpile meetings and automotive materials teams by the end of the week. If new entrants want to join the club, they will be judged first on reagent loops and tailings stability, and only then on cost per kilogram. All of this rolls into scenarios that are not prophesized so much as probability-weighted nudges. The baseline is the easiest to believe because it is mostly inertia. Through the late 2020s and into the early 2030s, global steel tonnage continues to grow modestly. Line pipe and structural steels keep preferring a few hundred grams of niobium per metric ton for familiar reasons. Stainless grades stabilized with niobium slowly expand in high heat duty where emissions controls demand longer life. The magnet world keeps buying niobium and titanium and tin wire as maintenance and expansion budgets allow. Existing Brazilian and Canadian operations execute incremental expansions, perhaps joined by one more value-added plant that climbs into higher purity oxides. Prices remain contractual and dull. The probability here is about 70%. The next scenario is growth with a new pillar. Battery anodes using niobium-rich oxides graduate from pilot into fleet-scale adoption for buses, delivery vans, mining equipment, and stationary storage that cycles aggressively. Hydrogen infrastructure takes a shape beyond press releases, pushing line pipe procurement toward low-carbon, niobium-strengthened steels with tighter weld discipline. A domestic project in North America or Australia actually closes a capital stack and builds with modern reagent loops, while one African project clears the governance and financing hurdles that have stalled so many. The market remains stable by design, but total demand rises enough that additional supply is not just justified but necessary. The price does not spike, it rises to pay for new chemistry plants and tailings built for 21st century weather. The probability here is about 20%. The tail risk cuts both ways and deserves honesty. A supply shock, whether from weather, a tailings incident, a prolonged maintenance misadventure, or a policy surprise, forces mills that can switch to practice their vanadium or heat treat playbooks and delays projects in hydrogen that need every mechanical property to behave. At the same time, a technological break in a corner of superconductivity or a more dramatic shift toward vanadium microalloying in key regions could shave a sliver off niobium's downstream share without handing back engineering wins easily. The system absorbs it, but the illusion of invulnerability evaporates. The probability of a disruptive detail like that is about 10%, with the caveat that disruption rarely follows the script you wrote for it. Production will continue to be a small cast with outsized roles unless and until a second act learns the lines. Brazil remains the riverhead. Canada remains the steadying hand. China will likely keep importing alloy for volume while experimenting at the edges of its own flowsheets. Australia, the United States, and parts of Africa are best understood as options that grow more valuable if battery niches scale or if policymakers decide that diversification is worth subsidizing through the risky phase between feasibility and first pour. It is fashionable to say that the geology exists. It does. The rarer thing is a team that can run a plant for decades without making headlines. For designers and operators, the advice is as unglamorous as the metal itself. If you need strength without welding drama, write down what you need in the language of properties and let your mill bring its niobium habit to the table. If you need magnets that work, ask for residual resistivity ratio numbers and reaction schedules, not brand promises. If you think your fleet hates downtime more than it loves range, give the niobium anode people a parking bay and a few buses with the keys left in. If your tailings engineer says, we should assume a storm we have not seen, say yes and find the budget. The pattern is obvious once you stop looking for fireworks. Niobium behaves for people who keep calendars, respect heat-affected zones, and design loops that close. Walk back to that bus depot. The second vehicle of the morning rolls in, panting a little, and the charger sings the same note. Somewhere far away a forklift is easing a 1-ton bag of ferroniobium off a pallet. Somewhere colder a pipeline crew is putting down their torches and brushing slag off a clean weld. Somewhere quieter a magnet is ramping, the helium is doing its job, and a patient is staring at a ceiling that looks like a children's book. None of them know they have something in common. They will not thank the grey granules by name. They will simply keep moving, on time, inside their windows, while a soft-spoken metal keeps doing the adult thing.